I'm only so involved with music in the way I am because I spent a sizable chunk of my life in the back of a band touring around playing my underappreciated stuff to people. So it's like I take great offense when somebody tries to pigeonhole it down that tightly. Just the way I am.
When Infantry played, I just lost it. I have a video of my friend and I dancing with her little sister.
Nice. To that song.
Back from like 10 years ago.
What 80s song is sampled in that? Trivia for you. Run DMC was famous for sampling songs. That's where the Beastie Boys, as were a lot of rap stars. Think about that. There's a great 80s song sampled in It's Tricky. And it's very, very popular. Very, very popular. All right. Let's get back into this. Let's talk about the errors real quick. What would a type 1 be? A false positive? Saying it's not random enough. What it actually is. Right? So I see type 1, even though the hypotheses have changed, it's still believing this when you should have believed this.
Yeah.
So you got some deviant data. And when I say deviant, I'm going to show you how you can get deviant data even with a purely random selection. So you're going to get non-random appearing data, say it's not random, but in fact, everything's working just fine. That's type 1. So type 2 would be, your false negative would be, saying your customers are out of their minds. Your opinion that your songs are not random enough is completely wrong. Go home. Your song's completely random enough, but they might actually be broken and you missed it. Which one's worse? Type 2? I think so too, because you haven't solved the problem and the problem does exist. You might piss off, and this is where Apple has a wonderful business model, which is amazing. I'm not sure if you guys are old enough to remember when Apple went away for a long time. Like Apple and PCs were kind of neck and neck back in the 80s and the beginning of like the microcomputer, like you could afford one to put on your desk. And then the PC world, because they allowed themselves to be created by other industries besides themselves, took over. Apple went away. I mean, it died. And then came back, rearing back with things like the iPod and whatever else. And they became they're a household name now.
They got rid of their Steve Jobs too, so when they brought it back.
They did bring it back, that's true. And part of that was his micromanaging of the company, of course. But
I'm sorry.
Sorry, I think I touched a nerve back there.
Was that
She didn't mean that, Steve. I know you're dead. So what I'm saying is Apple is very, very, very careful about their customers. I mean, they have to be. They're basically kind of on the tail end of survival mode. So you wouldn't want to make a type 2, I don't think. They'll upset them even more. And I've been told that they changed the randomizer algorithm because of the complaints. Whether or not it was random or not, they changed it to make it a little bit less random to appease people. Now, there could have been what you're talking about with the genres. That I didn't know about that. That could very well be what it is. But I'm not interested anyway. I just want to test to see if it is random enough. That's all I'm looking at here.
To make it less random?
Yes, to make it clump less, in other words. To get less clumpage than would be statistically acceptable. So, all right, so here's our data. Now, you guys over here had already started to crunch the data, right? Hadn't you? You'd already started to crunch it, right? You'd already discovered that here's what we saw, and here's what we should have seen. And Kate said if there's an issue with what we saw versus what we should have seen, it's most likely this one, which is the furthest over 5, or these guys, which are the furthest under. So in her mind anyway, I'm going to call this O and E if it's okay with you guys. I'm going to do O minus E. O minus E. Just little absolute differences. You can, but I'm going to do it manually for now, just because I want you to see what's going on and it slows it down to yes, eventually, and this is all we're going to use. But I just want you to this is such a different test statistic, and it's related to something you already know, but I think it's worth throwing back and actually looking at it manually. So let's just do this. There's no difference here, 0. That's 0. That's 0. That's negative 3. That's negative 2. Positive 2. Negative 3. Positive 4. 0, and positive 2. So there's our deviations. The modal deviation is 0, which, okay, modal deviation is 0. But that doesn't tell us anything, because we don't test modes. You can't test modes. You test proportions or averages. We decided to test proportions. Now, one thing you might notice, yes, when you sum that up, you're going to get 0. Michael referred to this right before the break. It has to be. It has to be because you learned that weeks ago. When I say weeks, I mean months. In 243 with Bert and Ernie, we did the exact same thing. We looked at the average and the deviation of each data point from average. When you summed that column, it always summed to 0. Because if this has to be 50 and this has to be 50, which they both have to be, any decrease on this side has to be matched by an equal increase above. It just has to work out. It's a balance. The idea of an average. If an average is at 5 and you've got some below the 5, you have to have some that total to that total deviation above it as well to balance out. I mean, it's the same logic for Bert and Ernie. It's the same exact logic. If you want to see an algebraic proof, we can totally do it after class. But just realize from a balance point of view, if you have everything balanced at 5, like right there, and then you take one chip and move it 2 down over here, you have to counter that distance of 2 on this side. Whether it's moving 2 chips 1 or moving 1 chip 2, you have to counter it. And then if you move 2 chips 2, you have to move 1 more chip 2 down over here to balance that, to keep that balance at 5. So that has to happen.
Or 2 chips 1.
Or 2 chips 1. There's all kinds of combinations, right? But the absolute deviation down versus up has to be balanced. So that -3, -2, and -3, what's that? +8, or -8, 2, 4, and 2. +8. They count. They cancel each other. So that's useless. We can't use that column. How do we deal with it in 244 or 243? What do we do with those deviations? We squared them. Exactly right. Same thing we do now. We're going to square them again. O minus E to quantity square. We're going to square the deviations, which of course creates the problem of distorting the deviations. The further away from average it is, it's exponentially now worse, but that's okay. We have a tool to deal with that. There's been a tool created to deal with just that. These are all zeros. That's a 9, 4, 4, 9, 16, 0, and 2. Don't worry about the sum of that. Because, oh, go ahead, Lauren.
The last one should be a 4.
That should be a 4. Thank you. Still don't worry about the sum of that, now the numbers are correct. It'll be the correct sum, but it's also something else to worry about. And this is the part I haven't found the history on yet. But the next move, and the only answer I have, is to match the distribution we're about to use. And that's not a very good answer. That's not a good answer, just so you know. But it's the only answer I've got right now. You take this result and you normalize it by dividing each of those by the expected number. So you take this column and divide it by each one by 5. I don't have a good answer for you other than that's how the function is set up, and I'll show it to you here in a minute so you can see the matchup of the function with it. But that's what we do to prepare the test statistic. It's kind of like a standard error, but it's not really a standard error. It's still a normalization. But what's weird about it is it's a squared versus a linear. And that just doesn't sit well with me, but it is what is used. That's the crappy answer, and I apologize for the crappiness of that answer. And I haven't found the research on it yet that explains it. Most stat textbooks go, here is the chi-square distribution. Okay, why? Here it is. Okay, so I'm still digging. Check it out in a couple months. So anyway, we just divide each of these numbers by 5. So we got 0, we got 0, we got 0, we got 1.8, I think. Check my math on these.
Yes.
What am I getting? I'm far down right now. 0.8, thank you. 0.8, that's 1.8 again. 3.2?
That's it.
Yes.
Is that right?
Yeah.
0 and 0.8 again. Add that up. That's your test statistic when you add that up. That's your test statistic. So when you sum this bad boy up, the summation of this silly looking function, let's see, it's 5, 7.4, 9.2? Did I do that right? 9.2? That is your test statistic. What distribution are we using? It's called the chi-square distribution. This is the third. You now finally get to circle something else besides Z and T on your template. Yay. This is the chi-square. Now, if you think about chi-square, chi is the big X looking thing, just the Greek letter chi. I used to get in trouble when I talked about Christmas back with the Catholic school for years and years. My friends and I talked about Xmas. Xmas, get yelled at by the nuns. You're crossing the name Christ out. I did some research in high school. It's actually not crossing the name of Christ out. It's the Greek symbol for Christ. So it's shorthand, Chris. Yes.
My dad.
Trivia for the day. Remember nothing else? Remember that? Yeah, here we go. I did not know until high school. I just got scarred by all the nuns.
What was that?
It's okay. It's okay. So this is the chi-square test statistic. 9.2. Now I got a question for you. If that were a T or a Z, if that were a T or a Z, and you got a 9.2 back, would you even bother thinking anything about the null hypothesis? You wouldn't, would you? Because 9.2 would be 9.2 what's? Standard deviations. And at that point you go, I just saw a 16-foot tall dude. Right? There's something's going on. That's what it would be, 9.2 standard. This is not, though. Because what's the smallest possible value this can be? What's the absolute smallest a chi-square variable can be? Go back to our chart here.
1.
Give me smaller than that. Close, damn close. 0. Why? Why is 0 the minimum?
Would it be because the observed and the expected could,
JC, nice and loud.
the observed column and the expected could match?
They could match perfectly. In other words, we run the iPod randomizer 50 times and we get exactly 5 of each of the songs. Not likely, but possible, yes? Not likely, but possible. So if these are all 5s and these are all 5s, zeros, 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 sums to 0. Fair enough? That has never happened in the years I've done this experiment, and I guarantee it never will. You'll see why momentarily. And with the more songs, the less likely it is to happen, obviously. Why can't it be negative? Because we took care of the negatives, didn't we? When we squared right here, we removed any negative values. So you're summing up non-negatives, zeros or positives. So this is a totally different distribution in that we don't have the negative and positive standard deviations. As a matter of fact, we don't even have standard deviations anymore. Take a look at this bastard. It's totally awesome.
But we're just talking about different. So
Yeah, exactly, but the question is, what is 9.2? Like, is it significantly different or is it not? It sounds significantly different because we're trained to think standard deviations, but it's not that. Here's what it actually is. Let me show you. It's totally freaking cool is what it is. All right. Close down. Okay, leave that up for a second, actually. Oh, you can't see that, can you? Hang on. Flowchart, don't need the flowchart anymore. There it is. Oh, he's beautiful. And he is. Brandon, if you don't mind, this would be huge. Thank you, sir. Did I just stop and start that again? I think I did. Yeah. The videos don't get too cumbersome. All right. There's the function for it right here. I know, and you don't have to memorize it. I needed it there in the spreadsheet while I was making the spreadsheet because I had to piece that together. What you're looking at over here is the actual function being created. Excel doesn't have a command for this to graph it, so I had to graph it myself by plotting points that are 0.25 apart. So you can see it's actually part normal distribution. E to the negative x over 2 looks-ish like a normal distribution, but we lost the squared bit on the normal. So you see how this thing is a little asymmetric? It's a little bit asymmetric. It's not a beautiful bell like a T or a Z. It's heavy to this side. It's heavy to this side. Now, notice where it also starts. It also starts at 0, which makes perfect sense. It can't go negative. It can't go negative. What do you think is happening the further along the graph this way we go? What do you... Say that again, Andrea.
it gets closer to your certain number, so it's like it goes on to infinity, but it's in touching.
Right, this goes off to infinity. What's happening to our iPod randomizer as we go this way?
It's like hearing the same song all
We're
the
hearing
time.
too many of the same song and not enough variation of all the songs. So clearly, perfectly random by 10%, like 10% of all the songs, a little bit of deviation from 10%. What's happening over here?
It's about there, yeah.
Right about here? Because right about, what have you done right about here?
That's your 5%.
You've cut off 95% and 5% JC. That made me very happy seeing that. It's like, yes, it's the same idea. It's the same idea as a confidence interval. It's just, where is the majority of the curve? It's right around here.
It's just, where's your data? I mean, it can't
Exactly.
just like here and here.
It's exactly right. Where did your data land? Now, our data landed right about here at 9.2.
Which is...
Remember what Kate said about her gut saying it's probably borderline? Now the question is, if that's 9.2, how much area is over here, because that's the p-value. Back here is the confidence. Over there is the p-value. And this is, I don't want you guys cranking this by hand. This is ridiculous. It's got degrees of freedom and the whole shebang. I wrote you a program too. But right now, we're going to slap it in here. We have 10 categories, because there are 10 songs. Now, see how the curve just changed a little teeny tiny bit? The curve will change, just like the t-distribution, with the number of categories you
Well, now
have.
our 9.2 looks a lot different.
It's okay. That's right. It's more usual, right?
Yeah.
What if we had 20 songs? What if we had 30 songs? Now all of a sudden 9.2 looks like it's too unusual.
Yeah.
Yeah,
But that's because we have too many songs. You need more deviations from whatever it is. So it starts belling out as your categories get bigger too. We'll come back to that. So we have 10 songs. Ha ha. We have a 9.2 test statistic. Your p-value comes out 42%. Huge p-value, yes?
So it's not abnormal.
It's not abnormal at all. Even with those goofy spikes at no effects and whatever else.
What about 2?
What about 2?
Well, forget it.
What 2
I
what?
was wondering if the number 2 is 2.
Oh, good. This goes back to Stacy's question. Suppose we had a test statistic of 0. Now 0, if you look at the curve, this curve is saying that shouldn't happen. You should not land at 0. However, the p-value based on this test would be 100%, because you shade, essentially, I haven't figured out how to make Excel shade this curve yet. What I'd like to see on this is your 9.2 here and then this whole thing shaded. I haven't figured out how to have Excel do that yet. So if it was at 0, you'd actually see the entire damn curve shading. But that masks what's actually going on. If that happened, I would take a look at the randomizer going, what the hell?
No.
Why did we just get 5, 5, 5, 5, 5? I mean, it's perfectly random.
That's when you look and say, oops, I accidentally clicked repeat instead of
Exactly. That's when the statistical test itself might lead you astray into thinking everything's fine. Or something else happened. This is what I've often said to you guys. Statistics often creates more questions than it answers. If that happens, then you take a step back and go, holy crap. It's like uber random, super random, artificially random. Maybe I've got the wrong setting on it or something like that. Is that fair? Ish. But why'd you pick 2 out of curiosity?
Well, I was looking at those numbers. We had one that came up twice.
Oh, I see. But don't micromanage the individual data point with the entire data set. You don't want to go into that data set. The only reason we drew this out over the entire board like this was to get that number right there. That's it. You can't go back and micromanage them in that way. Is that fair? Hopefully that answers the question better. Now, even if, so okay, let's finish the test out. I'm sorry, let's finish the test out. We got a big p-value, 42%. Does the iPod appear to be random? Well, it doesn't appear to not be random. So I guess that a different way, it appears to be random. And you say that anyway. Does that make sense? Sorry, it's week 9. I'm yelling too much.
What if test statistic?
Test statistic, chi-square, 9.2. We actually had that a couple minutes ago.
Yeah.
Chi-square is 9.2. Don't get too attached to that number 9.2 and its implied significance. Whereas a test statistic of, say, 2.5 on a t-curve is always the same. It's significant. 2.5 standard deviation is 2.5 standard deviation. 9.2 is going to change depending on how many categories you have. So that's where you have to kind of, don't get too attached to that number. It's a bit unitless, I guess is what I'm getting at. It's not like a standard deviation. It's a measure of deviation, but it's by no means standardized across the board for all chi-square experiments. Does that make sense? So don't be like, oh God, no. Don't get into that cat. Don't get into that worrisome kind of. And you won't, because it's week 9 and you're almost done. Not worried about it at all. Just trying to get through last week. So degrees of freedom is one of those archaic terms. It's 1 less than the number of categories you have. You don't have to worry about that. The program I wrote for you takes care of that for you automatically. You don't have to sweat that at all. I've seen more fist fights with degrees of freedom among statisticians. I'm dealing with right now at OSU. So don't worry about that. I've got it taken care of for you. Technology pretty much takes care of that for you. And the reason you have to concern yourself with them, and when I say concern, it has to be part of the process. Remember how the curve was changing? The curve changes as your number of categories change. So you have to make sure you're on the right curve. And the curve does, right up in here, K is the number of degrees of freedom in the curve. That's the only variable. besides your data. Your data is the x. But that k is the only other variable. So you have to make sure you've got the correct value of k in there so you're graphing the right curve. But I've taken care of it for you. You don't have to worry about dealing with that. And the charts that some people make you use are also taken care of for you in that respect. Cool? So we don't think anything's wrong. It does not appear the iPod is not being random. Or it appears the iPad is being random. So there we go. So what type of error could we make? It could be a type 2, which is the one we were afraid of, yeah? We were afraid of that one, right?
And the one that includes.
We were afraid of type 2. So, let's go one step, step 11. Step 11. If, you don't have to write this down, just talk about it conversationally. I'm sorry, talk about it conversationally. If you were worried, truly, truly worried about making a type 2 error, what would you do?
Change your number.
How?
Lower your confidence.
Lower your confidence. Lower your confidence. Because if you lower your confidence, you automatically increase your power of your test. So I've been kind of intentionally leaving out this phrase power. You'll see it on your last exam. It's one example of what power is, which is the opposite of a type 2 error. So confidence is the opposite of a type 1 error. 95% confidence means a 5% type 1 error probability. You'll see that on your exam for sure. That's one of the first questions on your exam. A type 2 error is opposite. The other part of that curve is called the power of the test. You'll very often hear about statistical power of tests. It's the power of statistical test. That's what they're talking about. It's the chance of not making a type 2 error. Which is, if you're interested in not making one, you want that power to be as high as possible. But the way to make that power as high as possible is to make the chance of a type 1 error a little bit bigger. Unless you want to get more data, which is always the best thing you can do. And with an iPod randomizer, of course, it's just keep shaking until you get enough data points. But in general, if you can't just create more data, lower your confidence, that also lowers the chance of a type 2 error. If you need more about that, look at the quiz. I'll have a solution posted for it this weekend, for the quiz that you guys, some of you guys just turned in, 2 of you I think turned in the power quiz.
How different would it be, let's just say, if we shook it 10 times, or 100 times?
100 times?
We did it twice.
We can take a look at that real quick if you want. I have a simulation based on 50, but I can double it very easily.
Okay,
So-
I really don't want to shake that.
Well, no, you don't have to. Watch. Kate, thank you. I don't want to either. Oh my God. Hang on. What I did was I made a simulator in Excel that tests it for us. So here's essentially the same exact experiment. So here's 50 shakes. And when I say 50 shakes, I mean
It's 50 random numbers.
it's 50 random numbers from 1 to 10. See, random between 1 through 10. So every time I press F9, I get another playlist of 50 songs. 50, 50, 50, 50, 50, 50.
But
So-
that's not using their software, that's.
No, that's using, but we just decided their software looks random enough.
Okay.
So I'm using a similar algorithm. I guarantee Apple's is better, just because I know Apple and how their care in their mathematics. But what I've done here is check and look up here. There's your p-values. Now remember, I just saw one go by. Did you see the p-value go by at number 5?
Yep.
That one flew by. Let's make it. We should see one how often? Oh, almost hit through it. How often should we see one? What percentage of the time? 5% of the time. Type 1 error, yes? Even when everything is fine. If you've set your confidence at 95%, you should get a p-value every 20 trials roughly, on average, yeah? So we saw one earlier, 4.9 or 4.6%, whatever that was. We just got a 2 point. Now look at that! That looks a hell of a lot like ours, doesn't it? But it's a little more deviant in that it looks like there's a few more that are too low or the ones too high. Notice they're all there. Have we seen one yet where there's a song that's not present? Let's see if we can find one of those. Ooh, look at that. Look at the p-value on that one. 0.99. There's almost that perfect agreement, right? That's almost perfect agreement. Pretty rad, pretty rad. 45%, 21%, 45. I want to get one where there's a song missing. That was almost our p-value. Oh, there's one. Oh, look at the p-value on that one. Son of a bitch. 10 occurrences of Billy Bragg. 8 of, I can't remember who's at 8 now. It's gone. It's too far gone. Pretty amazing, huh? Pretty amazing. Pretty amazing. Pretty amazing. So the idea is on every 20 shakes, you should see an outlier, which means a type 1 error. Because you're going to say, dude, the randomizer's broken. But that was your trial. You got that goofy outlier. You ended up in the tail of that curve randomly. That's the idea of a type 1 error. That's the curve. The curve you just saw is the null curve, the everything is random enough curve. And you can land out in that tail randomly. 1 in 20 times, Jamie.
Okay, this is just, I don't know, this probably sounds stupid. but,
No!
This is something that's been bothering me. Like, I understand, like,
Yeah, you do.
you would lower your confidence level,
Mhm.
you know, increase
Yes.
all of that, but if I was doing research and I was wanting to get the results published, isn't 95% like the lowest that,
Yes. Do you
So
know
why-
why? Do you know why it is?
Because it's been moving.
Because it's been handed down to us. I'm teaching you guys the standard by always using 95% confidence. I'm hopefully also inserting into your minds the ability to critical think and to ask yourself, sometimes you don't want that. If you definitely fear a type 2 error, you'd be silly statistically to forge ahead with 95% confidence all the time.
Okay,
It has been handed down to, it's not even 100 years old yet. It's been handed down, Fisher handed it down to us about 90 years ago. That's baby in the world of mathematics, right? And now, he even admitted, he's like, this is just a guideline. And you know what he called it? He called it a chance to take a second look at the data. That sounds like replicating studies, doesn't it? That does not sound like publishing anything. That sounds like, maybe there's something interesting here. Maybe we better press F9 again. Oh, right? That's what he talked about with 95%. He just picked it out of thin air, essentially saying 19 out of 20. It's pretty good.
But isn't that how you get people to replicate your studies, by publishing something?
Not necessarily. You should replicate it yourself if you can, if you have that. The problem is, when a study is published on outlier data, it falls apart almost immediately. And then statistics is played. It's not statistics, it's the representation of it. So Jamie, you are not, that was a great question, a fantastic question, and it's one of my biggest concerns with hypothesis testing. I'm giving you guys the tools, hopefully also giving you the wisdom to know when you have to adjust the tool. Like you're trying to put a number 3 Phillips head screw in and you got a number 2 Phillips head screwdriver, don't just keep,
so if
Go
you
find a number
adjust
3.
it- So if you adjust it because you don't want,
You adjust it, first of all, you adjust it beforehand.
okay.
And you explain in your abstract why you're going at lower.
Still possibly
Now,
get published?
yes, now time out. I want to say something about this too. When you read the journals that you guys have been reading, nowhere in there, very, very rarely in there, does it say, I tested this at 95% confidence. Much more commonly, they just give you the p-value, and the p-value is less than 5%. You saw a bunch of those on the very first set of articles I gave you. They don't tell you the confidence. It's implied they're testing at 95% because the p-values were all less than 5%. But if you get a p-value that's 16%, you might then report, but since we were testing at 80% confidence to avoid a type 2 error, then they're going to be like, oh, that's a perfectly logical explanation. What you don't want to do is get a big p-value and then pick your confidence. Whew, that's bad. Oh yeah, I was tested at 78% confidence. Got it. I mean, you don't do that. You pick it beforehand. Fair? And you'll calculate some powers on this exam you're turning in a couple of weeks, because that's where it gets fun, is figuring out that chance of a type 2 and avoiding it. Good. Fantastic question. Not a dumb question at all. Fantastic question. Yeah.
Off with that,
Yes.
an example of that would be like if they're testing a new medication.
Yes.
And they have the risk of hundreds of thousands of people dying
Yes.
because of said medication.
Avoid that like the
with
plague that it's trying to prevent.
Yeah, they need to change their confidence to avoid
Mhm.
falsely claiming it works.
Jesus, yeah, you do, yes, exactly. And that's why I love the interpretation of which one is worse, type 1 or type 2. Because sometimes type 1 is worse, sometimes a false positive is much, much worse. But with medicine, type 2 is often the culprit you want to avoid. Is that good? Oh,
Well, just
good, great question, Jamie. Fantastic, good question. Kate, if you don't mind, I'll build you a spreadsheet with 100 if you don't mind. Just email me to remind me. I'll just edit this one and
I
send it
was
to
just
you.
wondering how it would stable out with all the out.
It'll be less, you'll get far fewer of those close to perfect bars because you have more chance for variation. Michael, go ahead.
Could you just change this one right now?
I could, but I gotta change the random and I want to get, rather than do it, I gotta change it from random to, oh, you're still on 10 songs.
You could just, yeah.
Oh, I'm sorry.
I was
I thought you
thinking-
wanted more songs
No,
too.
I was
Yeah,
just
for
thinking
sure.
that if you did it the 100 times,
1, 2,
that your
3.
average is going to stabilize in an area more so than it just.
And there's 100 more. Let me just change the date real quick. I'm sorry, I misunderstood the question. We gotta select, oh, hang on a second, cancel. I gotta look at my, that was crap stuff. What is this? Count if, it's at E, that's E20, A2 to E20. Oh no, I did it. That's perfect. Apparently it updated it while I did that, because now all the functions are good. Nope, no it didn't. That's G. Shoot, I should have made it white. Hang on. Make it black so I can see what the hell I'm doing. There we go. Ah, here we go. Now we did 100 times, we need 20 occurrences of each, or 10 occurrences of each. There we go. You need to change something. There we go. Check the sums, equals sum of this. Make sure that's 100. Looks to be about 100. Yep. Looks to be about 100 over here. Yep. Let's check this p-value. This now has to be 19 and not 9. There we go. It should be golden now. So there's what you get.
We can't see that.
You can't see the p-value, I'm sorry. There we go.
Yeah, so it does stabilize.
Yeah, because you have more of those chances for it to catch up. That's what Dina was
And
saying
that's what I was
before.
wanting to see, is where
Yeah,
it
keep going to Dina.
stabilized.
I don't know why I started doing that 3 weeks ago. Yeah, it has more of a chance to catch up. That goofy I didn't see Pat Benatar until Psalm 24 is not going to happen with the level of frequency over more trials. It becomes exponentially less likely. Now, this was great. But hell if I want you to do all of this manually every single time, because that took us an hour to develop that. Grab your TIs, I gave you a program back in 243 called Goth. This is what it was for. Let's shut this down. Let's turn the screen off. And we'll show you how to get your test statistic and your p-value without using Excel and without cranking it by hand. Now, hopefully you can appreciate why I wanted to do it by hand. I mean, it's a beautiful test statistic. It's an absolutely gorgeous test statistic. It's also highly cumbersome as far as calculating it. Oh, here we go. This will work. So fire them up. I'm sorry, I lied to you a little bit. Don't run Goth right away. You have to put your data in first. You gotta put your, sorry. I'll explain to you how to get out of there if you have to. My bad. Getting ahead of myself. You first have to put your data. Sarah, you asked me a question about an hour and a half ago. Should I put this in my TI? I said no. Now I'm going to say yes. Because I'm a lying bastard. Let me shut the camera off and back.
I think the error arc